Okay, so I want to continue looking at algebra. So why are we looking at algebra? So what we're doing is we're looking at chapter 4 of the book, and really this is looking at the development of algebra in medieval Baghdad. And how is it developing? Well, we started like in around the year 820 with Al-Khwarizmi, who wrote his, he was the one who came up with, it's from him that we call the topic algebra. And so we see that how it developed was it came from geometry. So for Al-Khwarizmi, algebra was solving linear and quadratic equations. And he had methods for finding solutions, and the way they justified those solutions was by Euclid, which remember is the kind of like was taught as the epitome of logic. So if you could prove something using Euclid, that was rock solid. Okay, and then we went to I don't know how you say that TH. I don't know if it's a third or whatever. Covered even Cura in the late 9th century. So sort of like in the next generation, he sort of continued the work. He basically redid Al-Khwarizmi's work, but he would put things in kind of more general terms. So, so remember the way that they quite often showed formulas. So there were no formulas, but how you would do it was you would give an example, and then you would solve the example, and what you would do is if you had a different example, you would just plug in those different numbers and you would know how to come up with an answer. And Tabit did it kind of in a more general way. He'd say, you have, you talk about roots or thing or whatever instead of how we would say px. Okay, and now we went to Abu Kamel, who's like a generation later. He came from Egypt. I forgot to mention his nickname was the Egyptian calculator. And we'll soon see why that's a really appropriate title for him. And again, he wrote a book on algebra. So nowadays we call it a book on algebra. Of course, he would call it, so the book would be Kitab, and algebra was Al-Jabra wa Al-Mukabala. So that phrase, of course, wasn't turned into algebra until it came to Europe with the Latin translators. Okay, now what our goal is in doing this development is we're going to see how algebra goes from being geometric based to what we now think is algebraic based. But of course that doesn't make any sense, but maybe what we can more appropriate thing to do is it's more arithmetic based. And so what we're looking at is what we would call the arithmetization of algebra. And this is really the great Islamic contribution to algebra, to make things more like arithmetic. So, and you can kind of see how that can come about, hopefully, because at the moment we are stuck with just linear and quadratic functions, the polynomials. Well, we know polynomials can have any kind of degree, okay? And so if we want to look at something like, you know, x to the 4th minus 17 times x to the 5th plus 22, for example, we don't want to think of this as a geometric thing, right? We just want to go x to the 4th times x to the 5th is x to the 9th. You know, that type of thing is the process that Al-Khwarizmi had came up for arithmetic, also in the early 9th century. So his book on doing arithmetic really should serve as the inspiration for how to do algebra rather than Euclid. Okay, and it just took a bit of time for that realization to come along. And so after Abu Kamel, so you might be thinking this is out of chronological order, but these two guys, Al-Karaji and Al-Samawal, sort of go together. And then we'll come back to, he's also known as Omar Khayyam, who you might have heard of. He looked at the problem of cubics. And so that's where we'll end up with our discussion about this. And when we get to this, we'll see that how they treat cubics in this geometric fashion really doesn't do anything for us, right? It's kind of like a dead end. Okay, so let's return to Abu Kamel, the Egyptian calculator. So straight away we're starting to see advances, and what I mean by advances is this advance from geometry to arithmetic, because that's really the only way you can advance, right? Because if you're stuck with geometry, you're stuck with linear, quadratic, and then maybe cubic equations. But we're going to see, but of course we know that cubic equations don't work. We already know that, right? Because we know that you can't construct cube roots. That's the problem of duplicating the cube. It's the problem of trisecting the angle, which we already know were the big problems of the classical Greeks, the problems that they couldn't solve by straight edge and compass. Okay, so the techniques that would solve the quadratic equations cannot solve cubic equations. Okay, but Abu Kamel started working with powers higher than x squared. And he knew, right, that when you multiply things together, multiply powers, you add the exponents. Okay? He never stated anything like that as a rule, but you can tell by the expressions for what he called powers. So for x to the 5th, he called that mal shay, right, which is wealth thing, which is x squared times x squared times. So he didn't call it x to the 5th, he called it x squared times x, which means he knows that you just add exponents. Okay, so it's interesting that he doesn't think that it's important enough to state as a rule, but he just uses it implicitly. Like x to the 8th is mal. It's kind of like the spam joke from Monty Python, you know. And you know, he did all kinds of expressions, sort of algebraic kind of identities. And again, I want to emphasize that he didn't write these identities down as formulas as we did, but he would say things like when roots are added to numbers or subtracted from them, on whichever side they are arranged, then the fourth part is added. So the only thing there is he's talking about the rule of signs, that when you've got plus x times qx, that's the fourth part, is this thing here. So if this is a plus and a plus, or if this is a minus and a minus, this is a plus. He thought the rest of it was so obvious he didn't even need to state it. But it's interesting, you know, he proves all these kinds of things. These are all things to do with the distributive rule. Interesting thing is he did things with irrationals. So this one is kind of obvious. This one takes a little bit to think about. It's in the homework. You can kind of see where that comes from. So let's have a look at some of the problems that he gave, because as I said, they didn't do formulas, they did problems. So they would do a problem, give the solution, and then that solution would be then the information you needed to go out and solve a similar kind of problem. Okay. So here's something. So 10 minus x times 10 minus x is 100 plus x squared minus 20x. Okay, nothing too outrageous there. So Abu Kamel gave two proofs of this. So he gave an algebraic proof, which was just, you know, just multiply it out using the rule of signs, gathering like terms together, and you would get the answer. But he also gave a geometric proof. Okay, so here's the picture right here. So you let a length represent the number 10. You divide it at b, so you get x and 10 minus x like that. And then you complete the square as in the diagram. Okay, so there's AG, so GD is equal to AG. You make a square here. You make a little square here and a little square here. So this is x, is 10 minus x, that's x, and that's 10 minus x. Okay, so this square here is 10 minus x squared. And you've got rectangles. This rectangle and this rectangle is 10x. So what is it? So these little rectangles here are 10x minus x squared. So that means this gnomon added together is 20x minus x squared. And then the large square is 100. And the small square is the large square minus the gnomon. And you fill it all out. Okay, and you get the thing there. So the important thing is, you know, he does a geometric proof. He feels like he needs to do a geometric proof to show that even though he uses a kind of more arithmetic proof, that's not enough. He has to do a geometric proof. So here's a problem from his algebra book. Divide 10 into two parts in such a way that when each of the parts is divided by the other, their sum will be 4.25, 4.25. Okay, so putting that into modern terms, that means we've got x plus y equals 10. When each of the two parts is divided by the other, so that's x divided by y and y divided by x, their sum is 4.25. Okay, we know that this problem is a problem the Babylonians could have answered. So like 3,000 years ago, they were doing these kind of problems. And so the way he does it is he introduces a new variable z. You let x equal 5 minus z and y equals 5 plus z. And so the point is that with this equation here, you multiply both sides by x times y. So you get x squared plus y squared equals 4.25 times xy. So you substitute that into there, and you get 50 plus 2z squared equals that. And actually, so this is not using the quadratic formula at all. So this is a trick. By doing that substitution, you get just a linear equation in z squared. You solve it as z squared equals 9, so z equals 3. So that means your numbers are 8 and 2. Because 8 divided by 2 and 2 divided by 8 is 4 1/4. Great. Okay, so this isn't really anything kind of special. This is just kind of stock standard math that people have been doing for thousands of years. Let's look at a more startling problem. Okay, so this is a new problem that Abu Kamel came up on his own. One says that 10 is divided into 3 parts, and if the small one multiplied by itself is added to the middle one, multiplied by itself, the result is the large one multiplied by itself. And when the small is multiplied by the large, it equals the middle multiplied by itself. Okay, so so the first thing we do when we're analyzing it is first we just write it as what equation. So we've got 10 divided into 3 parts. So let 10 equal x plus y plus z. And let's arrange it so that z is the biggest, bigger than y, bigger than x. And we're going to make it positive. Okay. The second equation is that z squared equals x squared plus y squared. And the last equation is xz equals y squared. Okay, so that's 3 equations in 3 unknowns. So we know we've got a chance of solving it. So what Abu Kamel does is he uses that rule of false position, which is an old method. Again, it goes back to the Mesopotamians and the ancient Egyptians. They would do it. So basically what you do is you assume an easy answer like 1, and then solve it, and then you blow up the answer afterwards. And the reason why this works is if you look at it, each equation, the terms of it have the same power. So here, each of the terms is quadratic. Here, each of the terms is quadratic. So that if you blow up the answer by, say, b, you replace y by by and x by bx and z by bz, you'll see the b's just cancel. So this method of false position works for these kinds of problems. So if we let x equals 1, so that just simplifies it so that we've just got z squared equals 1 plus y squared, and z equals y squared. So that gives us a nice quadratic equation, which we know how to solve. Y squared, z equals y squared, well, the roots of this is just by looking at the appropriate case algorithmic, and y is the square root of that. Okay, and so now we do 1 plus y plus z. That's supposed to be 10, and we see that it's definitely not 10. Okay, so let's say it's a, and so if we let b be 10 divided by a, then that's the factor that we need then to blow up the solution to get a correct answer. So if we multiply everything by b, we've got a solution. Okay. Now the problem is that b is 10 divided by this thing here. Let's write that down. Okay, so to finish off the problem, we're going to rationalize it. We're not going to do that because it's really hard. But I hope you're kind of impressed by this. This is, he's the Egyptian calculator, right? So he must have been somewhere on the spectrum, I guess, because he does this kind of problem and he just proceeds to happily do it. To rationalize this, well, what he did was he proved that B was a root of this quadratic equation here. So the fact that he did it that way is, the interesting thing about it is that he is treating a quadratic where the number is something irrational. And to do that, he uses like this identity here, which is not 100% obvious, but if you go back, where is it? It just follows directly from this square root a minus square root b. So that's just a plus b plus or minus that. So if you go ahead and do that, you get this identity here. Okay? And so once it's a quadratic equation like that, again, it's one of the forms from Al-Khwarizmi, so you just know what the answer is, and so you can rationalize this to get that. Okay, so it's pretty cool. It's just, but the thing is this arithmetic or is it geometry when doing this algebra? It's getting to be more and more arithmetic-like. It's in treating these things here, this is hard to justify in a geometric way. It's kind of more treating the objects like arithmetic objects rather than geometric objects. Okay, and so it's pretty cool. So this is showing some sophistication. It's showing treating problems. I mean, these are kind of not your everyday quadratic problems. It's really pushing the boundary of what we can solve with algebra. Okay. Another problem of Abu Kamel is the problem of birds. And he wrote a whole book on this, the problem of birds, and it's nothing to do with birds, really. It's this kind of problem. With 100 dirhams, we buy 100 birds of 4 kinds. Geese at 4 dirhams each, chickens at 1 dirham each, pigeons at 1 dirham for 2, and starlings at 1 dirham for 10. Okay. So this is going to be 2 equations in 4 unknowns. So we know that there's not going to be a unique solution. But we know that the answers are going to be integers, positive integers. And so it all depends, if you let A, B, C, D be them, you've got to look at things mod 4 and mod 10. Mod 2 and mod 10, and you've got to create a whole bunch of cases, and there's 98 possible solutions, and he goes through how he got kind of sorted that out. He even did similar problems, but so here was his justification for why he wrote this book, The Problem of Birds. I found myself before a problem that I solved, which I discovered a great many solutions. Looking deeper for its solutions, I obtained 2,676 correct ones. My astonishment about that was great, but I found out that when I recounted this discovery, those who did not know me were arrogant, shocked, and suspicious of me. I thus decided to write a book on this kind of calculations for the purpose of facilitating its treatment and making it more accessible. I think that's hilarious. He goes around telling people that he found 2,676 correct solutions, and I'm sure the people said, yeah, sure, okay. And so he was miffed at that, so he wrote a book about it. So that's the Egyptian calculator. let's go on to our next guy, Al-Karaji. So he wrote, he wrote around 1000. He wrote a book which is called either the Marvelous or the Glorious. There's the Arabic word. So it's the Marvelous or the Glorious on algebra wa al-Mukabala. He was a Persian, but he worked in Baghdad. He wrote on binomial coefficients and Pascal's triangle. So I think he was the first one in the Islamic world to work on that problem. So in fact, earlier when we looked at the problem of finding square roots or cube roots, we needed Pascal's triangle to solve that. That work comes from Al-Karaji. So interesting thing, he's one of those people that's claimed that they were the first to do mathematical induction. But you've got to be skeptical about that. The reason why you've got to be skeptical is because if we look at how notation and things are developed, they really didn't have the notation and techniques to do a proper mathematical induction proof. So I know a lot of you have done in foundations, you would have done a proof by induction, and a lot of you are comfortable with that. That's actually a pretty sophisticated kind of mathematical argument. And they just didn't have that know-how technology. They obviously understood it. They kind of knew that they were doing something, what they were doing with mathematical induction, but it's hard to say, yes, that's actual mathematical induction, even though it's kind of clear that that's what they were thinking, that was the way their thinking was going. But anyway, we'll return to that later. At the moment, we're talking about algebra. So he's really considered like the real pioneer of this concept of arithmetizing algebra. Although we've seen, right, beforehand, with the previous mathematicians, that they were kind of reaching towards that sort of idea. Here's where Al-Karaji did it kind of like a really bright thing. And it's a reason why algebra, doing stuff with polynomials, is basically arithmetic. So just like Abu Kamal, he talked about higher powers. And so, so the shay or thing, that's just the unknown, the x. And so you talk about mal cube, mal cube, etc. So again, he knows he's not using x to the cube, x to the 4, x to the 5. He's thinking of it as, when he's calling it mal cube, he's thinking of it x squared times x cubed. So he knows that you need to add exponents. But he calls these things orders. And that's the important concept, because order is the same word that they use to describe powers of 10 when you're talking about the Hindu Arabic numerals, right? So remember, if we write something down 3, 2, 1, that's 3 times 10 squared plus 2 times 10 plus 1. These things were called orders. Oh, I shouldn't use x, should I? The center dot. Okay. In the same way, we can think about 3x squared plus 2x plus 1. These things are also orders. So once you think of a power of x as an order, all of a sudden you're making it like arithmetic. Okay? Because now you can use the algorithms that you did arithmetic on they now transfer over to do things with arithmetic on polynomials, right? So we can add polynomials, right? Because all we have to do is add the coefficients of the corresponding order. We can multiply polynomials together, right? Because we know that when we do 3x squared times 5x cubed, you get 15x to the fifth, right? Because this is the second order, this is the third order. Multiply something together, you get something of the fifth order. Okay, so you can do addition and multiplication, but the thing is, you can now do other things that you can do with arithmetic. You can do division. You can do taking roots of polynomials. Okay, and these are things that really make no sense from a geometric point of view. So to do these things, you have to completely treat it as arithmetic objects. The number common to all orders is 1. What does that mean? Well, that just means 1 to the n equals 1. And interestingly, just like arithmetic, you can get fractions, right? So to each order is the corresponding part with the property that any order times its part is 1. So that means for every x to the n, there's an x to the minus n, or 1 over x to the n. And so when we multiply those together, we get 1. Okay? And so now instead of thing, mal, cube, mal, cube, we can also talk about part thing, which is 1 over x, part mal, which is 1 over x squared, part cube, part mal cube, etc. And so what happens when you do arithmetic, if you do division, of course, you know, what happens when you divide one number by another and that number is not a whole thing? So for example, if you do 3 into 2, it goes on forever. And so if you're going to divide a polynomial by another polynomial, it also might sort of go on forever. So what you might get as an answer could be, you know, 6 part thing plus 6 part mal plus 6 part cube, etc. Okay, and so for us, this is the same thing as a Laurent polynomial, right, where we can have negative powers. They don't go arbitrarily high, but they can go sort of like to negative infinity. Okay, so our Karaji, this is a really bright thing that he came up with. And so he tried to do arithmetic with polynomials, except he had a little bit of a problem. Okay, so for example, he knew that so you want to do arithmetic on polynomials, you've got to know how, you know, you're doing something, you know, you're doing something with two polynomial things, and you want to combine them to get some coefficient times some power there. I don't know whether you're dividing it, taking a square root or whatever. Okay, so you've got to go from coefficients of your inputs to the coefficient of the output, right? So, for example, he knew that A minus B is A plus B, but he had one problem, which was when you were subtracting a negative thing from a negative thing. Right, that minus A minus B equals minus, and in brackets, A plus B. That's the kind of rule that he screwed up on. So he didn't quite work it out perfectly. He almost got it. And so that's where I'll stop. And the next person we'll talk about is Al Samawal, who fixed Al-Karaji's problem. Can anyone tell me anything about Al Samawal from his name? There's a couple of clues in his name. So it's not son of would be Ibn, but he's Ben. Ben Yahah, Ben Yehuda. Does anyone know where that comes from? It's Jewish, right? That's from Hebrew. And Al-Maghribi, that's where he's from. That's like Spain. Anyway, we'll talk about him in the next class.